Hello, hello, Wilston Scholars, and welcome to another episode of BC Calculus with Henry Lombino. Alright, so today we're going to be working on another AP problem, yet again. This is from the 2013 exam for your response. It's number 2. This deals with something that I hope y'all remember, which is, this is polar curves and graphs and finding the area of those and the integrals of those. So it's a blast. It's going to be some fun. Alright, so the graphs of the polar curves are showed of r equals 3 and r equals 4 minus 2 sine theta are shown in the figure above. The curves intersect at theta equals pi 6 and theta equals 5 pi over 6. So let's do A and let S equal be the shaded region that is inside the graph of r equals 3, but also inside the graph of r equals 4 minus 2 sine theta. It's the shaded region. Find the area of S. All right, so this is an integral problem. In a normal one, this would be find the area underneath the curve, but with a polar curve, it's a bit different because because r is the radius, and so it's going around in a circle as the angle increases. So if you recall, the area for finding the area of a polar curve, the area of a polar curve, the way you find that in integral is going to be that. So it's 1/2 of the integral of r squared d theta, because yeah. So that's that. And so we have to find, but the problem with this, of course, is that there is an intersection here. Luckily, they give us the intersection. So let's break this down. I like to do this problem by breaking it down into two parts. So we have these two. So we have, if you look at this graph, we have these 2 points. Let's zoom in on this. We have these 2 points here. We have pi 6 and 5 pi over 6. Pi over 6 and 5 pi over 6. And we're going to draw in. So that is where the two equations meet up, and thus the circle starts to change. So the way I'm going to do this first problem, where we have to find areas, I'm going to break it down into two parts. I'm going to find this area right here, and then I'm going to find the rest of this area out here. And yeah, that's how we're going to do this bad boy. Just erase that. Alright, and that's how we're going to do this. So let's zoom out a little bit again. Oh god. Okay. So yeah, so let's first do the integral from pi. So let's do first the integral of, so this circle here is the integral of r equals 3. So that's actually a really easy integral to do. Let's do that integral. So the integral is going to be from pi is going to be equal from 5. It's going to be the integral from 5 pi over 6 to pi over 6, because it starts here and goes all the way around to here. And it's going to be of 3 d theta, 1/2 d 3 d theta, and then we're going to add the integral from pi over 6 to 5 pi over 6 of, and this is squared. Whoops. This is squared of 4 minus 2 sine theta squared d theta. And that's our area right there. So I'm gonna do one of these you can do out actually kind of easily. This one over here, and when you do it out, you're going to get, well, actually something should strike you fairly quickly, and that is that this right here you can actually figure out just through logic. The distance between these 2 points, 5 pi over 6 minus pi over 6, is equal to 4 pi over 6, which is equal to 2/3 pi over 6. What does this tell you? It tells you that that is 1/3 of a full circle. And you know, since this is just a simple circle with radius 3, you know that the area of the hole inside of that circle is going to equal pi r squared, or it's going to equal to 9 pi. And you want to find and you're going to want to find that you're going to want to find 2/3 of that, because 1/3 of it is missing. This 1/3 right here is the missing. The 2/3 that are left are what the area we're going to try to find, and that if you multiply that by 2 divided by 3, you're going to get 6 pi. So that's your answer. Then, I messed these up. Whoops. The bounds, this should actually start at the end of the end, because the end goes first, so this should be 5 pi over 6, and this should be 5 pi over 6. Pi over 6, I'm sorry, I'm a little bit out of it right now. But, yeah, so these integrals, this should be just pi over 6, this one right here. So those are the actual integral signs, because, yeah. And so you get 6 pi plus 1/2 5 pi over 6 of 4 minus 2 sine theta squared d theta. You're gonna plug that into a calculator, making sure that you change your graphing to polar. You can do that in like the mode function, and the answer that you are going to get is 24.709. And there you go. Alright, on to B. Okay, for part B, particle moves along the polar chord r equals 4 minus 2 sine theta, so that at time t seconds, theta equals t squared. Find the time t in the interval 1, t is greater than or equal to 1, less than or equal to 2, for which the x-coordinate of the particle's position is -1. So what this is asking for you to do is to solve the x-coordinate in terms of t. Now, this is a polar function, so you're going to have to solve for x. Now, if you remember, the way you convert it is x equals r cosine theta. That's the conversion formula. And then we are also given r is equal to 4 minus 2 sine theta, and theta is equal to 2 squared. So if we plug all those in, we're going to get x in terms of t is equal to 4 minus 2 sine t squared times cosine t squared. Okay? Then And then from there, we're going to be looking at, we're going to want to solve it. It's asked for when the x-coordinate of the particle's position is -1, so we're going to plug in -1 for x of t equals all this jazz. Again, and then what you're going to do is you're going to plug this into your calculator, and you're going to solve for t, and you're going to find when t is for what value of t does that equation equal -1. Pretty simple, pretty easy. It's just a bunch of substitution. You just have to make sure that you remember this right here, that this transformation from polar coordinates to Cartesian coordinates. All right, on to C. All right, in C is asks for the particle described in part B. So we're going to be using part B in this. Find the position vector in terms of t. Find the vector, the velocity vector at time t equals 1.5. So this is basically turning this problem into a parametric equations. That's what they're called, parametric equations. And so you found the equation for x in terms of t, but now you have to find it in terms of y t. So once again down here, we know y is equal to, the y coordinate is equal to r sine theta. R is equal to 4 minus 2 sine theta, and theta is equal to t squared. So you're going to get y in terms of t is going to be equal to 4 minus 2 sine t squared. Could plug in the t squared for theta times sine t squared. Yeah. And there, and then the position vector is just putting it into vector, taking that and taking your x vector from up here and turning it and putting it in vector form. So you're just going to do this. It's going to be 4 minus 2 sine t squared times cosine t squared, comma, 4 minus 2 sine t squared times sine t squared. Done. There's your position. So that's your position vector right there. That's your position vector. Sorry. All right. And now asks for your velocity vector. Your velocity vector. The best way to do this really is to just find what the velocity vector essentially is I'm gonna do velocity vector here. Velocity vector is going to be equal to x, the derivative, damn it. The velocity vector is essentially going to be the derivative of x at 1.5, and then comma the derivative of y at 1.5, and you're going to want to use your calculator to solve that. And so when you you're going to plug those numbers into your calculator, use the n derivative formula, and you're going to get the numbers of negative 8.072 and negative 1.673. And we're done. There are final answers for all of those problems. So again, this is just kind of a nice cross between parametric equations and polar equations. Hope you enjoyed it, and I'm almost out of time, so have a good day. Bye.